Well, how did you do with this question? The best estimate is just the mean, and so we calculate the mean. We add up all the measurements, divide by the number of measurements, which is 5, and we get 200 parts per million.
So, I have added our best estimate, and I've called it h with a line over top, and we often do that. We indicate that something is a mean by putting a line over top of it. Don't confuse that with a vector symbol, which is an arrow. And we have this best estimate, but I hope you don't believe that we think the door frame is exactly 2.235083333333333 meters. No. If we were to redo these measurements all again, we would presumably come up with a slightly different answer, and that tells us that there's uncertainty. So how many of these digits are significant figures, and what is that uncertainty? What range do we think the true value actually lies in? We think it's close to this mean that we've calculated. So there are actually two separate issues. First of all, what's the uncertainty of each individual measurement? And that's not quite the same as what the uncertainty is in the best estimate itself. So the underlying idea of an uncertainty is that it's a range that you believe the true value might lie within. So if I measure something and state that it's 4.6 plus or minus 0.3 meters, and then you measure the same thing, and let's say you don't know an uncertainty, but you get 4.8 meters. Well, is this surprising? No. Your measurement lies within the range that I stated the value should lie within. And so your measurement is consistent with mine, and we shouldn't be surprised by it, even though it's different from what I stated as my measurement. So an uncertainty tells us a range of variation, so that if we repeat the measurement, we expect to see values lying within that range. Well, we can see something about the range of variation because we've taken multiple measurements, and so we can see directly that there is a range of variation. So a first attempt at answering what's our expected range of variation is just directly from that data. If we make a measurement, we can expect another measurement to be within about 4 millimeters of our first one. But that's our maximum range of variation. It looks like it's pretty rare for two measurements to disagree by that much. And what we're more interested in is what's the typical range of variation. One way to think about the typical range of variation is to realize that we sort of expect our measurements to cluster around the mean. Measurements in the middle of the range should be the most common. And so we can think in terms of deviations from the mean, right? You can calculate a deviation from the mean just by taking a measurement and subtracting the mean from it. And so if you do that for all of the measurements, you get a bunch of different deviations. Well, now we want to know what the typical deviation is. Well, just as a typical measurement is the mean, you might be tempted to say, what's our mean deviation? Won't that be a typical deviation? So I'm just going to take an average of all these deviations. Well, that's really, really, really tiny. In fact, that's down in the range of the floating point algebra of the computer. So in fact, it's quite possible that the answer here is 0. Why? Oh, well, the mean is in the very middle, and so there should be just as many numbers above the mean as below, and we're tending to get a whole lot of cancellation. And you can in fact show that the mean deviation has to be 0. So that's no good. So we don't want all this cancellation. So one answer might be to say, well, why don't I take absolute values of the deviations? And that is certainly an option, but there's another way of doing it that's the accepted way. So the accepted way is a thing that we call the standard deviation. And it's kind of a little bit like what I just suggested, right? The problem here is that we had positives and negatives canceling each other, and we don't want that. So another way to stop that from happening is to square our deviations. Then in the end, we're going to have to take a square root so that the dimensions are right. So it's basically a mean squared deviation that you then take the square root of. There's this detail of an n minus 1 instead of an n down here, and that's mostly so that if you do something really silly, like try and take the standard deviation of a single measurement, the formula gives you nonsense. But there's another technical reason as well. So we are going to take this standard deviation as a measure of the scatter in the data, and that means it's an estimate of the uncertainty in each individual measurement. So let's get the standard deviation. So we're taking more or less a mean squared deviation. So first of all, I'd better take all my deviations and square them. And then I'm going to sort of take the mean of those, but I say sort of because I need to divide by n minus 1 instead of n, so 11 instead of 12. And then the standard deviation is just the square root of that. And there is my standard deviation. Now I'll just say, again, there is an internal function of the spreadsheet which would have let me do all of that in one step. We've got a standard deviation, which I've called sigma sub h, of 0.00124 blah blah blah, a bunch of other digits that probably don't matter, meters. And just notice, my original naive estimate of my uncertainty was 0.5 millimeter. This is showing that in fact the precision I'm getting with these measurements with a measuring tape is an uncertainty of a little over 1 millimeter. Now, that is an uncertainty. We know this is an uncertainty in the individual measurements because it's a measure of scatter of measurements, typical differences between two measurements. But that's quite different from what the scatter in the mean is. So data set A is the one I've been working with. Data set B is another set of measurements I made. And you see, of course, it didn't come out quite the same. And so we can now start to talk about how much we expect the mean to move around, right? In these two sets of measurements, I get means that are very similar, but they're not quite the same. On the other hand, this measurement set C is not an actual set of measurements. This is one that I made up to illustrate a point. And what I've done is these arrows are indicating the standard deviations, and I've made a set of measurements where its mean is about a standard deviation away from the means of the other two. Now just think, if you had done these two measurements, and then you actually did this measurement and came up with this one, would you be happy with this set of measurements? Does this look like it's a set of measurements of the same quantity that these ones are? I don't think so. This looks like we're measuring something else. So we don't expect the mean to move around that much, and this is telling us that the standard deviation isn't a good estimate of the uncertainty in our mean. We need something else. And this something else is called the standard deviation of the mean. In statistics, it's often called the standard error. And this is the thing that we interpret as the uncertainty in our best estimate, or in our mean. And all you do is you take your standard deviation and you divide by the square root of your number of measurements.
Let's check your understanding of this so far. So here are these measurements of concentrations of a contaminant again, and I've calculated the mean, standard deviation, and standard deviation of the mean of them. And I want you to decide which of these statements about how we interpret these numbers is true.